Um, how are you gonna stay on the Zoom? If you can tell me if there's like a question in the chat that I missed, that would be great. Yeah. Huh? I don't think we can just shift everyone to the front. All right. It is not recording. I think. Is it?
Yeah, you don't know when
Okay. As long as.
you look at the green dot. Yeah, so you look at the green dot where the green bar is.
Oh, yeah.
Yeah. Look at your share. Yeah, my name. Because I literally recently did this for
All right, let's go. Hello. All right, let's get started. Sorry we're a bit late. I took a bit too much time relaxing, and then we ran into last minute technical issues with the wrong Zoom link. But I blame Tara for that. So let's get started. So I'm not sure how long this is supposed to go for, but I will try to see if this can go for around like 2 hours approximately, give or take. Hopefully take, because I don't want to overload with your brain with too much information either. It's gonna be heavily improvised. I haven't prepared like I've prepared things, but it's not like everything's set in stone or concrete or whatsoever. What I want to go through today, and then it can change based on what you guys feel more comfortable or like what you guys are more in need of, I guess. But my rough outline for the day is we're gonna start with pointers because they're arguably the first big concept that people start to struggle with, I guess. Pointers, and then dynamic memory, and then something else that's not as common in code, but could pop up in your exam because it's more theory based, is time complexity. So recently, Tron1 has been introducing more data structures, algorithms, and with that comes the concept of time complexity. And I wanted to speak a bit more about that and how you can analyze the runtime of functions so that you can write about it in your exam if it comes up. Not that I know if it comes up or not, because Mitch rightfully does not trust me with the exam questions. And I think that's the right move. After that, I wanted to go through a data structure. I am not sure which one I'll go through. The options are a linked list or a stack or a queue. Linked list is arguably the most appropriate one here, but I'll probably come back to that when we get to that, because a lot of you would have implemented linked list already in assignment 2, but also if you're here for a crash course, there's a chance you guys didn't properly understand the linked list. So we'll come back to that. I'll ask the class what data structure they want to see the most of. And if we have time, maybe we can do 2, like a linked list and a queue, or a linked list and a stack. And then at the end, I have an example question that I prepared that does a bit of everything. So file input output, dynamic memory, bitwise operations, and then just normal string manipulation, I suppose. So let's start with pointers. Okay, so we're gonna start with a simple number. My favorite number is 14, so I'm gonna say x is 14. Hope you all know the syntax of a pointer by now. So int star pointer. That's the syntax. It doesn't really matter where you put the star, but I would like you a bit more if you put it closer to the data type, because that's what makes sense in my head. So this will point to somewhere in memory that contains an integer. So right now, if we want to point it to something, we got to take the address of a variable that has the data type int, and then we got to actually take the address of it. So x, what we just defined, is a number, right? We want to point to it, which means we need the address of it. And to take the address of a variable, we use the ampersand operator. So that's how you go about it. And let's have a look at pointers in action. So x right now we know is 14. All right. Whoops. We'll print it out. And then f. Let's just do the pointer for now. So x is 14, and then our pointer gives me minus 983320004. So I want to give a shout out on why that's the case. Kendall, who is not in this course. Yes. Okay. Yeah. So this is actually the location in integer form. But I hate to be that guy, but that's not actually the address of it. If you wanted to print the address, it's actually %p. Yeah, so that's the actual address where int x is stored. But if we want to actually look at the value that's inside, we have to dereference the pointer using a star here. Let's go back to printing an integer and then compile and then execute. All right. So now x is linked to my variable called pointer. And every time I make a change between these two, the change will be reflected in the other variable. So if I change x to 15 instead of 14, and then I do the exact same print statement here, we should expect to see that it's changed, right? I didn't touch the pointer variable, but because I've changed the variable that the pointer is pointing to, the variable, when I dereference the pointer, it has changed. Everyone clear on that so far? Cool. And it works both ways. So if I go star pointer is equal to 22, and then I go x, actually, let's just do this. That's how it works. Yeah, I dereference the pointer, change the value, and if I go back to x, the value has changed. Cool. All right, so let's introduce a third variable here, int y, and then let's say it's gonna take the value of my pointer. All right, so my pointer declared. Oh, whoops. That was a quick panic attack right there. We'll get past that. So y is now 22, right? But what if I changed this to 23 and I come back to y? Should the value change? Just give me a nod or a shake of the head. Should the value change? Luke's shaking his head. Anyone nodding head? No. Cool. Yeah, the value doesn't change, right? This was actually a trick question that I was given in when I did Tron 1 the first time, I believe. They introduced two variables and then a pointer, and then they played around with my feelings at the start. And at the end, they were like, which variable is like pointed to? Does this value change? So for the people who got this, great job. So with that said, we're going to get to more pointer and array relationships now. So you get a comment saying that a pointer is just an array or array is just a pointer. It's kind of true, but the concept, if you were to get a bit technical, that's not strictly the case. So the way it works is, let's say I had a function called modify array, right? And then I take in an array, let's say of 6. So I have a function, goes through every single element, and all it does is adds 1. Right? And then let's put in an array here, int my array 6, 4, 2, 4, 8. I got 6 numbers here. And then I'm gonna pass it to the function and let's see what happens. So modify array. Modify array, and then let's print it out. And I'm gonna comment all these out so that we don't get confused with anything. So the original array was 4, 8, 15, 16, 20, 42. And then we can see that everything has changed here, right? So clearly you can see from here that the argument I'm taking is an array of size 6. But the thing is, I could have done this and it would have worked exactly the same way. So the way it works is that in memory, when you make function calls and you pass in parameters, the way the compiler works is usually it takes a copy of your variable. I hope you remember the swap tutorial exercise from like week 5 or 6. Because it makes a copy of the variable, when you're dealing with arrays, it's very inefficient for the compiler to make, let's say, 100 copies if your array was size 100, or 10,000 copies if it was even bigger. And it's just really not efficient. So the way the compiler gets around that is by taking the address of the very first element in the array. And then because arrays are contiguous blocks in memory, as long as you have the first element, you basically have access to the rest of the array, right? You don't know where the array ends in memory. So you just get a pointer. You have to specify how many elements are pointing to be pointed to, but it at least avoids the issue of copying everything over again and again. All right. So if I change this to int star, everything still works the same, right? And to show you how that works in memory, let's say we have char, I don't know, s. So I have an array of characters, essentially a string, but let's just do this without printing it out. It should give me an error. I hope. If it doesn't, I'm gonna be embarrassing myself. It does. Okay. So let's have a look here. All right. Actually, let's just quickly go back to this definition. So instead of a pointer, I'm explicitly defining the size. These are all just what you expect, but this very last error is what I want you to look at. So even though I've defined it as my array /6, you can see that the compiler is actually expecting an int star. So even though you've specified the size, you know that it's always going to be expecting a pointer, which is where the relationship between pointers and arrays come from. Any questions so far? No? Okay. Oh, hey, Lucas. All right. Yeah. Another thing I would like to point out is like, if at any point you have a question, feel free to stop me. I could just keep going on and on. So, and don't be embarrassed of asking any questions. All right. So, we now know that an integer array x int star, right? So that means theoretically, instead of passing in my array like this, which does work, from our understanding, you should now able to see that doing this should also work. Exact same thing. So I don't know why this works. Yeah. All it needs is the address of the first element. And then in my function, I specify, hey, just go up to 6 elements. So it works exactly the same. So that's how the relationship between pointers and arrays work. Not much more to go on pointers apart from that. So I'm going to assume everyone's okay with this for now. Yeah, some nods. Was that a shake of a head? No. The girl behind Amelia, I don't know your name, but yes. Okay. Let's go through passing to the array, I guess. I don't like that variable naming. Multi-array, let's say. So this is how you declare a 2D array, I guess. And then we can do I think that should be okay. Let's see. Let's find out. Whoops. All right, compiles. Let's see if we can print it out just for a sanity check. I hope you'll get what's going on there. All right, so that's our 2D array. Before I move on to passing into a function, everyone understands what happened there? Yeah. Okay. So the way 2D arrays work is slightly different. Even I have to Google it sometimes, but let's just see how it goes. Let's see if we can double every element in an array. So once again, you can explicitly mention the size of it. So our matrix is 3 by 3. Yes. Okay, I think that should work. So functions called double array, and then let's see if I can pass in multi-array. All right. Whoops. Cool. So every element has been doubled. You have to explicitly specify the size. You can still go ahead with pointers if you wanted to. So if I want to get rid of this here, I have to say int star star. And the way it's going to work is in memory. Um, 1, 2, 3, 4, 5, 6, 7. In memory, this is how your 2D array looks like, because in memory, it's like just one contiguous block of stuff, right? But if I asked you if you just received the pointer to the first element of the 2D array, how does the compiler know where the end of the first column is? Or how does it know how many rows there are? Does anyone want to take a guess? It doesn't. Yeah, I'm not sure if that qualifies as a trick question, but it doesn't. So if I were to just pass in int star star my array, I kind of have to specify how many rows and columns there are, or how many elements at the very least. So if I change this to an int star star to reflect my new function prototype, I have to explicitly be like, hey, yeah, go 3, 3. Is this gonna work? Is this gonna work? No. Okay. This will not work because in C, how's the best way to put this? Only one dimension can be unknown. So for every dimension you have, you can think of it as like a star or pointer, right? So if you have a 1D array, you have int star. If you have 2D, it's int star star. 3D with your images from assignment 3, you have star star star, right? Because your screen is 2D pixels and you have RGB, it becomes 3D and you have star star star. But the thing is, when dealing with data, C can only deal with at most one uncertainty in the dimensions. I think I said that right. So you have to actually specify how it's going to work explicitly. So if you're faced with a scenario like this, where you only can pass in an int star star, one way to get around it would be to use dynamic memory. Because when you use dynamic memory, you're only dealing with pointers. And as you can see here, pointer to a pointer is different to a pointer of 3 elements. So this error message is saying we expect int star pointer array, I guess. Great. But instead we've given it just the first pointer. So this is where I say where the difference between pointers and arrays become a bit more evident. Because technically speaking, an array of pointers that contains 3 pointers is not the same as a pointer to a pointer, right? So if we want to go down this road, let's just use dynamic memory. So instead of specifying 3 here, let's go ahead and use an int star star, right? So straight off the bat, we know this is where our 2D array is going to live. We know that it's going to work with this function because it expects an int star star, and we're giving it an int star star, right? Most of the errors I've seen students struggle with this semester is quite literally a mismatch in data type, sometimes with the number of stars that they have. And the thing I always tell them is just to like try to equate the number of stars you have on the left and the right. And sometimes it's as simple as that, right? So let's create this 2D array dynamically now. So you got to imagine this as one big array with 3 arrays inside. And we need to actually allocate memory for the bigger array first. So I hope you remember how dynamic memory syntax works. It's in the standard library. And I will take int star star. So it's good practice to typecast. If you don't typecast, it's not the end of the world. I think it will still work, but it's just good practice. Malloc is the function that you will be interested in. You can use calloc as well. Shouldn't really matter because you're going to change the values anyways. And the argument to malloc, if you don't know, is the number of bytes that you expect it to have. So let's look at this here, right? We're trying to allocate space for our big array. So we need to figure out how many bytes that these arrays inside would take up. And remember, each array, because we're dynamically allocating them as well, all they need to be is just a single pointer. So what we need to do is allocate space for 3 pointers so that those pointers in return can be allocated with memory for the other layers, the inner layers. So to get the number of bytes of a data type, we do size of, and then the data type. In this case, because it's an array, I'm going to do int star. And because there's 3 of them, I'm going to times it with 3. Any questions on that so far? Yeah. Okay. So a good rule of thumb that I like to follow is however many stars you have here on the left, you have the exact same number on the first time on the right, because, well, this is a typecast and it has to match. and then the inner one reduces by 1. So because there's 2 stars here, there should, by good rule of thumb, there should only be 1 star here. Yep. So here we're creating space for 3 pointers to integers. Okay, so we've created this at the stage, right? We create this at the stage, but the thing is the pointers themselves are not pointing to anything. So if you want a actual 2D array, you gotta allocate space for them as well. So we gotta go through every single pointer inside. And allocate space for them. So malloc again, this time because they're pointers or arrays, we do int star malloc size of. This time we're allocating space for actual numbers because we're allocating numbers for each of them, and inside we expect something like 0, 1, 2 actual numbers as opposed to arrays again. So we're gonna do size of int. And how many do we want? It's up to you, but again, we're gonna do 3. We're gonna go with 3. So it's gonna be size of int times 3. And you can see here that I'm still following my rule of thumb. Whatever is on the left, so each element of multi-array is an int star. So int star matches int star, and then the whatever follows inside the size of has 1 less star. Yeah. Yeah. And then we can fill up again. I'll just fill it out with like 4 or something. I don't know. Bear with me while I think something. Okay, let's hope this works. Nope. Subscriptive value is neither array, no pointer, no vector. Interesting. Hang on. I just used the wrong variable. There we go. Once again, another slight panic attack, but I like to think I kept my cool. Cool. So that's our 2D array. And then now we can pass it into the function, which is what we're building up to before. So now let's say double array. And then now we can pass in the 2D array that we just dynamically allocated. And instead of all 4s, we should see all 8s. Is that a hand, Lucas? Okay. All right. Yes, Has. Yep. I can simply go bam, and now it's in the public workspace. Yeah. Any questions about what we just went through with the dynamic memory? Yeah. Okay. Yes. I don't know your name. No, but the guy behind you. Sorry? Like instead of 4s, no. Yeah. Yeah. Like here, instead of filling each of them with 4, I fill them with no. Oh, yeah, yeah. something like this. All right. First of all, there are a lot of things wrong with Python that I would like not to get not to that I would like to not get to today. But let's just print this out, right? So we allocated space. It has the space. It has the capacity to hold elements, right? And then we're gonna manually define it to be this instead of allocating it like this, right? What's your prediction? So like an compiler error or like a not just unexpected behavior? Okay, so compiler error, yeah. You have a prediction? Anyone else? Yeah? Okay. Whoops. There we go. The fuck? Point me to the line. Oh, there we go. Yeah, okay, thanks. Oh my God. I think the folio above is fine. Hang on. Yeah, no, it's definitely here. Am I just fine? Does anyone see an error? Just checking. What the hell? The answer is it shouldn't work, but I'm not sure if this thing is happening because it shouldn't work. Expected expression before. I have a theory. I think so as well. Yeah. Because I'm pretty sure it's expecting a pointer to a pointer, and I'm giving it an array. Again, to bite me in the ass on what I just said. Pointers and arrays are technically not the same thing. That's what I did before, like at the start. Oh, okay. Yeah, I guess we can go through that. Oh, I just don't want to delete this. I'll clean it up after. You mean like this, right? Okay. Let's just try with actual numbers for my own sanity check. Thanks. There we go. Multi-array undeclared. What? There we go. Okay. Happens to the best of us. Okay, this works. Okay, so now let's try it with a bunch of nulls. Oh, whoa, yeah. The answer is no. Yes, nulls are only for. Are you familiar with Java? Okay. Okay. To use some Java terms, there's like primitive types, which are like your ints and your chars and whatsoever. Then like this everything else. With that points in C specifically, it will be pointers. In Java, it will be like classes or wrappers around primitive types. But basically, only things that you can point to can be null, because a null signifies you don't have like a memory address, and integers and characters are considered primitive, so they don't contain an address. It's only the pointers that contain the address, so you can't point integers to null. In Python, you can go x is equal to none and then make it a 7 later, but that's just because Python's broken and no one likes it. So yeah. Just quick things up. Again with this. Again with this. Yeah. Okay, we're back to where we were before. Okay. Let me just remove this thing. Oh my god. Okay. Hope that's clear with the null part. Yeah. Okay. Last thing with the dynamic memory that you should be aware of is freeing. So when you, especially when you have nested freeing, you should always be looking to free from the innermost layer, I suppose. So whatever you malloc last, you want to free first. So here I malloc the big array, right, to hold the arrays first. And then I allocated memory for the arrays inside. So when I free, I want to free from the arrays inside first, and I want to free the rest. So if I'm done, so that's going to free each one, and then I'm going to free the entire array. And hopefully that won't give me any compiler errors. Okay, thank you. Cool. So that is pointers, arrays, and that. Yes, Tilly. That's like asking like, trying to think of a good example. Kind of. So to get technical, all your pointers are stored in the stack. So imagine this is the stack, and then you have your pointers here. So you have multi-array. Then you have first array, second array, and third array. Remember, everything you see them as nested, but in memory it's still like one block. Like everything just still happens, right? And then every time you dynamically allocate memory, the reason why you dynamically allocate memory in the first place is, one, you may not know what happens in runtime. You want to save memory. 2 because you want to avoid a stack overflow. So your stack is where your function calls, your local variables are made. And actually, this might be relevant for your exam as well because memory is a big part of C. So I would advise listening to this. All your local variables and function calls are made on the stack. So when you have like recursive functions that keep going on and on and on, creating new variables each time, you get a stack overflow, right? Or during runtime, if you just keep increasing the size of your data, your stack will overflow, right? That's where dynamic memory comes in. Dynamic memory gives you memory from a different part of the, I don't know what the word is, computer, big memory, I don't know. But there's a different part of memory called the heap, right? The heap is a bunch, like so much more bigger than stack, I suppose. So when you allocate something dynamically, your pointer is on the stack, but the uh, but the elements that you're actually filling out or like the actually allocating goes to the heap. So the 0, 1, 2, 3, 4, 5, 6, 7, 8. Imagine these were 0, 1, 2, 3, 4, 7, 8. First will point to here, second will point to here, third would point to here. And then if you free multi-array first, you could lose access to these 3, and which in turn you might lose access to these elements, which means they get stuck on the heap. Whereas if you free this first, so if you free first, you lose the connection between here and here, which is what you want. So as soon as we free this, these are gone, right? Whereas if you free this, these might be gone. Oh, actually, shit, I'm sorry. First, second, and third are also on the heap because each array that's inside is also still dynamically allocated. So it's actually first, second, third, right? First points here, second points here, and third points here. Got that so far? Right? So if you free this, you lose the connection between this and these 3, which means you have these left over. Does that make sense? Yeah. Another answer would be in every other language. I say that as if I know a lot of languages, but I'm mainly referring to Java here. There's this thing called the garbage collector in Java, where at the end of every program, like, as the name suggests, it collects garbage, like anything that you don't use like dynamic memory over, it like cleans it up. Whereas C is kind of like, so yeah, so Java's like when you're the last child in the family and the family picks up after you. And then C is like when you're the first child in the family and then the family's like, you take care of this yourself. We don't really care. You should know what you're doing here. Oh, this is touchscreen. Okay. Does that make sense? Okay. Yeah, so stack and heap, I would advise you to know. Yes. What's your name again? Hey, Ben. Hi. Oh, were you the guy I convinced to change the Tron? Oh, sorry about that. I apologize. Okay. Well, I think you made the right choice, but in case I accidentally ruin your life, I apologize now. Do you mind if I share it with the rest of the class? Your error. Sorry? Oh, it's gone. Okay. I was gonna say I could bring it up here, I guess, but Are you comfortable with sharing it? 3 or 2? I'm gonna take a wild guess and say you're Richie. You know around when that might be? I probably shouldn't be doing this actually. Actually, yeah, no, you know what? I shouldn't be doing this because like there are people who haven't submitted the assignment yet. Okay, we'll come back. You can find me sometime later. But if you can describe the issue, I can try to replicate it, I guess. How late was it? Nice. You can define stuff within function. You'll just lose it once you're out of that function. So if you've defined that to the array in the function and you try to use it outside of it, then your compiler is gonna be like, the fuck you were referring to, bro? Yeah. Yes. What's your name? Sorry? Global highly unencouraged. Yeah. Why? Okay. So it's will be hard for you to see why it's bad in your assignments and tutorials and stuff, I guess. But once you get to big projects, and I'm talking like industry grades, and you have like 5 different source folders, and each source folder has like 10 .c files, right? You want everything to be encapsulated within like each file. And if you have globals or worse, if you start using like externs and stuff like that with globals, it's just like the conflicts that come with it, and it's very hard to track down, I suppose. Yeah, like I can see why people would be like, oh, I can just use it here. Yes, theoretically you can. It's just that once you move on to greener pastures, you will encounter a lot more issues. Yeah. Cool. Yes. Sorry? To not use globals. Yeah. Yeah. So what you could do is something along the lines of let's say an array, right? You could do something like int star create array. So in the function here, you create a local variable, something like that, and then you return the pointer to the array. So that would work. So you created something in the function, but because you're returning the pointer to it, that's fine. Or if you want to modify things in the array, actually, yeah, as for modification, it will be like we just did here. You declare it first and then you pass it through. Yeah. And also, if you do move on to greener pastures, which I hope you do, um, high chance that you will not be working with C. You might be working with C++, in which case there's more elegant, nicer looking ways to handle this. Yeah. All right. Sorry, one sec. I know it looks bad that you just walked in and you saw me on my phone, but it was just a 10-second break, I promise. All right. Okay, so that's a majority of pointers, arrays, and dynamic memory, I guess. Let me just rename this to pointers, dynamic memory. All right, before I move on to the next concept, any other questions? Again, this is like very flexible, so if you have specific questions, I'm willing to just try it out here for a better understanding. Nope. Yes. So think of your assignment 2 actually. So assignment 2, your program technically never ends, right? It's a server, right? And then online people can't see this, but like imagine this is the amount of memory you're using, and as a server, it gets bigger and bigger and bigger, right? And then you want to minimize the use of memory because if you're using a lot of memory, things get slow, right? But what if your program never ends, like assignment 2, right? So every time you have something that you don't need anymore, you want to free that immediately so that the amount of memory usage gets lower, and then you get a more faster efficiency with your program, I guess. Yeah. Yeah. Sometimes you simply cannot afford to wait until everything's done because your programs are run and executed within like 1 second, but in the real world, it's just not that simple. Yeah. Okay. All right. Let's move on. I want to talk about time complexity. So time complexity is a more theory-based, I guess. I can't comment on if it's gonna pop up in the exam or not. Again, I don't know. Mitch doesn't trust me enough, but it's a good thing to know. The Tron degree doesn't offer data structures and algorithms as a course unless you do computer science. So I think it's a great idea that he's introducing a bit now. Let's see if I can do something here. Okay. All right, let's see how this goes. So we got standard input output. And then I'm just gonna include time.h. Don't worry about that for now. You'll see why in a bit. So the premise of time complexity is my code, let's say, executes well, like does the job, and Luke's code executes, does the job, and Sophie's code does the same thing. But we all use different ways. How do we compare in real life without test cases or whatsoever which algorithm is the best to use? Mostly when we speak about which algorithm performs better, we're talking about time complexity and space complexity. I'm not going to go through space complexity that much, but for like a one-line summary, space complexity is how does your memory usage change as your input size gets bigger. Time complexity, on the other hand, is how does your runtime grow relative to the input as the input gets arbitrarily large, right? So with time complexity comes this concept of big O notation. So big O is how you determine how fast it's how we classify the speed of algorithms, I guess. And we'll speak about that in just a bit. But let's start with an example. So let's say I have a number called n, and it's 100, right? And I want to check the sum of the numbers up to that number. So if I have 10, I want to calculate 1 plus 2 plus 3 plus 4 plus 5 plus, 10. So int sum n. All right. Now a trick question. How would I calculate the sum of all numbers up to n? What's the first thing that comes to your mind? Yeah, for loop, right? So let's say int answer, we start from 0. Cool. That everyone understands that, right? I hope. So printf d slash n n. So all the sum of numbers from 4,009 up to 100 is 4,950. Cool. Let's search up sum of natural numbers. Let's look at this. So it turns out the sum of the first n natural numbers is given by this formula, right? So theoretically, I could do the same thing, right? So instead of sum here, I'm going to call it sum 1. And I'm going to do sum 2 here. Okay. And then the answer this time is going to be, what was it? N times n plus 1 divided by 2. And let's do the same thing. Thank you. Once again, another mini panic attack. There we go. Okay. So there were 2 different ways to figure out the sum of the first n natural numbers. Which way was more efficient? The second one. Why? Yeah. No. So in terms of time complexity wise, we consider division to be the same as multiplication. Yeah. If we go all the way down to technical, like all the way to like assembly level or like electronics, Verilog, FPGA levels, then yes, division is a bit more time consuming. But when we talk about modern day time complexity analysis, division is the same. Yeah. So this is what we call constant time. O1. So runtime is always the same. Yeah. And this is what we call linear time. Runtime grows linearly with the input. Yeah. And to prove that, I'm going to use something a bit fancy. So under time.h, and it's okay if you don't understand this, there's like a data type called clock. Again, on. So basically, I am getting the time before I start the algorithm. I'm getting the time after I end the algorithm. And I'm going to do the exact same thing for the other function as well, but name it begin 1, begin 2. Cool. So if I want to see the amount of time it took, I just gotta subtract. And don't worry if you don't understand this part, because pretty sure it's not accessible. It's just something I'm using to show for demonstration purposes. Okay, let's see. What? Thank you. Nice to see the attention. All right. So algorithm algorithm 1 runtime is 42, I think it's like 0.0000042 seconds. I think that's like, I don't know, 4.2 microseconds, 42 microseconds. I don't know. You see the number, but this does not necessarily prove that algorithm 1 is slower than algorithm 2. Why is that the case? Like, I've given you the numbers. Algorithm 2 is like clearly shorter, as like more efficient, but this does not necessarily show that algorithm 2 is more efficient. Why is that the case? Yes. Yeah. You have to check how the runtime changes as the input grows, right? There's a chance that algorithm 1 right now, even though it takes longer, there's a chance that if the input grows, it stays the same, or it just grows at a much slower rate than algorithm 2. So you can't just test with a single number. What you have to do is see how the runtime changes as your input size changes. And now we can see that it's actually not as efficient, right? We can go to million. Whoops. It's an overflow there. Hang on. Yep. We can see when we go to like, let's multiply by a factor of 10, algorithm 2 stays the same always. So constant runtime, and then algorithm 1 is increasing linearly. Yes, Has. Yes. Yeah, but the growth is the same. Your times in second will never always be the same, just because that's how computers work. Any questions on time complexity so far? Yeah. Like code it up using clock and stuff? No, you definitely would not have to. The clock that I use here is not accessible. It's just something I wanted to show so that it's a bit more clearer, I suppose. It's usually not, once first starting out, it's not as easy to see how algorithms change speed over time. And I thought this was a good way to show it. All right, so to continue on a bit from there, here are like a few runtimes, I suppose. So we already heard of constant time. There's log n time. So log n times usually happens when you're dividing in half again and again. So if you know about binary search, if you have an array, you start from the middle, and then you go to the other half, and you go to half. So something like that is log n times. Or something like traversing down a tree, like a binary tree, because you only have 2 children, you go to one side each time. does an O log n time. Took me a while to understand that, so I hope you understand that. We got linear time, and then with linear time, you can just increase the polynomial as many times as you want. There's quite popular quadratic time for most sorting algorithms. Your number can go up to whatever, as I guess. And then there's exponential time. Basically, most of the time you want your code to be like around here. There's also O n log n, I suppose. Yeah, most of the times you want to be around here. There's been a couple times of work where I present an algorithm to my supervisor. He looks at it, it's like, that's quadratic time, not good enough. So I had to like lower it down to one of these here. With that said though, it's also important, like with theory in exam, again, I don't know what happens there, but like I assume something would be like guess the runtime of this function, right? So let's have a look at something like this. Let's say we have an array, and then I'm passing it in, and I'm giving it the size or how many elements there are in an array. I don't know if you remember this, but this would be when you did like a tricky square assignment or challenge or something. So this is what this does. What is the time complexity of this? Anyone would like to go? N squared. Why? Yeah. So for each input, you're going over it twice. So this is quadratic time, right? What if I change that? What's the runtime now? What's the time complexity? Sorry? 5n? Okay, that's what you say? Oh, actually, maybe it's good you didn't see what I changed. Maybe just have a look with fresh eyes. What's the runtime of that function? Sorry? I can't hear you. Oh, what? Okay, all right. Anyone else want to give a guess? Okay. Sophie is 95% correct, I would say. She said 05n, technically true. So for each input, you're going over it 5 times. So yes, it is 05 n, but in the computer science world, yeah. Yeah. So in the computer science world, we don't worry about constants. So 5n is the same as n. Yeah. So if it doesn't matter if you had 10,000 n. Yes, but on like a lower level, it will make a difference. But again, big O notation, runtime analysis is when inputs get infinitely large, right? And at infinity, you just don't care. So this is actually ON. Sorry? Yeah, get rid of the constant. Yeah. Yes. So let's say something like all right, let's say we print the first element. I want to know where the halfway point is. And then I want to print a square, let's say. So what I've done here is print the first element. Then I'm printing half the array. And then I'm printing a square. All right, runtime, someone. N squared plus n on 2. Okay, anyone else? Oh, that's the point of this, right? Possibly. We'll come back to that. Do you have a final guess, Ben? Okay. Tilly, do you have a guess? Okay. Oh, okay. Just piggybacking on his answer. Okay, cool. All right. So the answer is actually just O n squared. So yes, this is technically speaking, O1 from the printing of the first element. We have O n on 2 from printing half the array. And then we have n squared from printing the square. But it reduces down to O n squared because yes, we get rid of constants, but we also get rid of anything that's not as big as the biggest term. Again, as you get infinity, it doesn't matter that there is an extra n on 2 term. When you have an n squared, it's going to overtake it. Yeah, always keep the biggest one. Yeah. So, get rid of everything. Yeah. So if your exam has a question like endless runtime, instead of giving this, you're gonna want to give this. Yeah. All right. Last one is practice for time complexity. Something I came up with. Probably doesn't make sense, but there's still a runtime there. Maybe take like a good 20 seconds to look at it. And you can tell me what you think the time complexity is. Are you looking at me because you have an answer, or do you just like looking at me? I'm talking to you, James. Okay. Why? Yeah. So the main thing to look out for here is the half. Basically, what this is doing is you're just taking a number and then you keep dividing by 2 until it goes to 0. Yes. No, it's fine. Like it's still log. Yeah. I say that with 98% certainty. You might want to double fact check that. But I am 98% sure it's still log, and even if it's dividing by like 3. Yes, the thing you have to consider here is this is a bad example I just came up with in the spur of the moment. I'm curious myself. When you're curious about things like this, just give it a go. It does get to 0. Just chops up, surface crack. Yeah. Yes. Yeah. But even so before, if I had changed the %d to a %f, it was still given a 0, just because that's how the data type works, because I used an int in particular. Then yes. Yeah. I don't know. I didn't hear what you said, but for Tilly, yes, if I did change it to a float, it would just keep going until eventually it gets to like the smallest that the float can take, I suppose. That's my educated guess. Yeah. Quite a bit, unfortunately. Yeah. Why? Are you doing computer science as well? Okay. Yeah, computer science, data structures, algorithms, algorithm design, models of computation, those subjects are all quite math heavy. Yeah. There's more written assignments than there are coding assignments. So, yeah. All right. I'm gonna move on from time complexity. Anyone, any last minute burning deciding questions? No? Yeah. Yeah. Are you asking why is it n log n? It's best explained visually. So the way merge sort works is it keeps dividing, right? And even though it divides here, it's not like the entire process of dividing all the way to the end is log n, right? So when you're here and you go all the way down, once you split everything up into single element pieces, you're at O log n because you divide everything, right? And the way merge sort works, it then goes over this entire list of single elements and then adds it to an array. But to do that, it goes over everything once. So there's your linear part that comes in. So there's an O and log n. There are some videos that explain it really well that will do a much better job than me looking at a diagram. But the simplest way I can put it without much like an animation is like, yeah, log n to split all the way down, and then in the merging part, that's where the linear time comes from. Yeah. I still have online participants. Nice. Oh, MJ's here. Okay. Okay, I really didn't think it would take this long, but I don't want to spend too much time. So we've done these. I assume we only have, if we want to end it at 2 hours, I assume we can only have time for one more of these. So I am just gonna look at you guys and ask you, would you rather have a data structure implementation or an example question that kind of goes through a bit of everything? And I'll show you the example question so that you can make your so that you can make your decision a bit easily. Basically, with the example question, actually, hang on, just give me 1 sec. All right, with the example question that I came up with, it's, as it says here, it's a one big basic dumb examples. Basically, you want to take user input on how many lines of text you get through the command line. And then basically there is, you want to put them into a specific format. I'm a big superhero fan, so forgive me here, but you're gonna put in 2 strings, an integer and a decimal. Again, these are done through the command line. And what we want to do is dynamically allocate space for them. Dynamically allocated because you're giving it to the command line. What we want to do is we take the integer number, do some bitwise operations. In specifically here, we're just doing bit masking and bit shifting. And then we take that extracted number with the bitwise operation and write it to a file. And then we are gonna add one more, and then which would test your skills with appending to a file as opposed to writing to a file, and then reallocating with dynamic memory, which we didn't go through, to something that has already been allocated. So this should test your knowledge on pointers, arrays, string structs, file IO, dynamic memory, scope, type defs, and bitwise operations. Because it's like one big dumb example. It probably won't make sense in the long run, but like the elements are there. Or we can work on a specific data structure, either a linked list or a queue. What would people want? I'm gonna give you like 30 seconds to ponder, and then I'm just gonna be like, whoever wants to do this, raise your hand. Whoever wants to do this, raise your hand. What is that hand for? Like specifically just bitwise, or as part of the question? Okay. We'll come back to that in a bit. Let's see what the others think first. I'm gonna give you like 30 seconds while I make sure like no one has died on my phone. Okay. I'll see if I can squeeze in bitwise separated for you, but I would like to go to at least one of these first. I might come back to bitwise at the end if we have time, or if you're still interested and you haven't like burned out your brain. So, people in the chat, feel free to comment as well. If you would like to do a data structure implementation, raise your hand. That's a very weak hand, Luke. Raise it nice and proud. Okay, cool. That does not necessarily mean the other one will get hands. If you would like to do the example question, raise your hand. Wow, okay. Cool. All right. Sorry, Luke. All right, we'll do the example question. If it makes you feel any better, for the example question, sorry, for the data structures we didn't get to go through, what I can do is I can just paste in data structures that I've implemented into the workspace so that you can go over it, I guess. There's some comments on there, and hopefully that makes sense. So I'll just paste that in, and then we'll do the example question instead. Okay, so example question. Let's briefly go over it again. So from the command line, we want to enter a number, which is how many lines, how many in this case, superheroes want to keep track of. And then each superhero is an entity. So we'll use command line arguments. Each superhero is an entity. So we want to make use of structs. And because we're getting the number of superheroes that we're going to account for through the command line, which is dynamic, we have to use dynamic memory. And then we have extracting some data from the number that comes with the superheroes. So we're going to do some bitwise operations. So for example, if I pass in 38, and fun fact that no one will care about, the reason why I choose 38 is because the first Superman issue was released in 1938. Moving on, 38 in binary is 100110. What we want to do is take bits 2 to 5. So for example, 2, 3, 4, 5, which is 1001. And then write that number into a text file along with the name itself. So 1001 is 9, right? So we're going to do that. And then once everything's done, we're going to take one more input to practice our appending to a file and reallocating memory. And this is the example. So it should ask how many superheroes will you be entering. I entered 3. So I put in 3 superheroes worth of data. And then it's going to be like 3 superheroes accounted for. And then we're going to add one more. And then the file created should look something like this, with the string, the superhero name, and then the number from the bitwise operation that we do. So let's have a look. First thing we want to do, int main, int c char star. Okay. First thing we want to do is define how we're going to store this. So we want to use structs. So struct. And then the 4 things we want to store are 2 strings, an integer, and a decimal. So name. I could technically dynamically allocate this, I guess, but I'm not going to do that because I don't want to. So I'm just going to define a buffer and say, hey, it can be at most 100 characters long. So that's the superhero name. And then let's say the secret identity of them. Gonna use the same thing, buffer. Why did I? Okay. Int year is for the year that they were published, I guess. And then float. I really don't know why I have a float here. It's just to add variety. So I'm gonna say favorite decimal. That makes no sense, but I'm gonna do that anyways. Okay, so this is the struct that we have. You don't have to do this, but I personally like to type def my structs. I don't like to type struct superhero my superhero because that's a bit too long. So type def, I hope you know, is defining your own data type. So if I type def here, whatever I type after is immediately defined as what's here, whatever's in the middle. Convention is to just use the same name so that you don't get confused. So now instead of typing struct superhero my superhero to create a single struct, you can now just do superhero my superhero. Clear on type def so far? Okay. So first of all, we want to start with how many superheroes? Entering. N. If you're in my class, I probably tell you not to use scanf as much, but I'm gonna use it because it's easy. And if it's with numbers, it's technically okay. It's with strings when scanf fucks up a bit and cause you a lot of problems. So scanf send d/n. don't forget you need the address to the variable. Yes, Ben. F gets. It's just a bit safer. Yeah. All right. So that takes, we now have our number of superheroes. We want to store them in dynamically allocated structs. So we need an array. And because we don't know how many we want, we need to dynamically allocate it. So we want to have an array. I'm going to use an array of pointers each time. So I have a double star here because I want an array of pointers to superheroes, and then the pointers are dynamically allocated struct. It is technically fine for me to do this as well. I'm just gonna choose not to so that I can show you more things. Yes. Like this. Yeah. So that specifically happens with characters. Thanks. Sorry, I'm gonna go off course a little bit because I want to show this as well. Thank you. Yeah, that doesn't matter. Oh my God. Let's get rid of this. Okay. Let's enter two characters. I'm gonna put in X and Y. X, enter. Y, enter. All right. The Y never got printed. Oh wait, hang on. I sent C here. Sorry. I just want to emphasize this. X. There we go. The change I made was this was %D before, so I was supposed to scan a character, but X I put in and then enter, and I don't even have time to put in Y. It immediately goes to the next one. Anyone know why that's the case? Yes, Sophie. Yes. So when you're typing a single character, for us, we just type in X. But the compiler takes X and then /n, along with a carriage return as well, actually. So in order to force that to not happen, that's when you add in that space. The fuck? Okay, I don't know what happened at the end there, but we got the X and the Y. Let's leave it at that. But that's why sometimes you have to put in a space. You only have to do it when you're scanning single characters. Yeah, because of the issue of when you press in and enter, it takes in as the second character. Yeah. What happened here? I'm not too sure, but I'm not gonna get into it. Sorry? Sophie's correct. Nice, once again. Cool. Let's get back to what we were doing before. But that is something good to know about strings and characters. Once again, your stars should match on the first typecast. And then you have one less star here. And then we gotta store every data that comes in. So we need to create variables for that as well. So user input, let's say, buffer. So the reason why I'm doing this here is this user input is the entire line that I put in, right? And then we want to separate it into 4 different parts, right? With the spaces. So each space, this goes into a variable, this goes to a variable, this goes to a variable, right? Hope everyone gets that. So what we want to do now is get user input for however many superheroes that we want to account for. And however many we want to account for is in n. So we're going to loop through n. Okay. So for people who are not aware, string.html, cool. F gets the argument, you have 3 arguments. The first argument is where you're going to store it in, the variable you're going to store it in. So user input. The second variable is how many bytes you expect. Our user input string we said is can only hold up to 100. So we're just going to say 100. And then the third argument is where do you expect to get this data from? And for us is stdin, that stands for standard input, which is just the terminal. So now we want to split the string into 4 different parts. Splitting the string, you can use Strowtalk if you want. I assume that's what most of you are used to, but I'm going to show you something else. Has anyone used scanf before? Yes, nice. So for people who are unaware, scanf, let's look at the documentation. All it does is take a string, and then basically whatever you want to split up into, you write the format specifiers for that, along with where you want to store it. So if we want to split up our user input string, that's the first argument. And then whatever you want to split it into, you put the format specifiers. So it's going to be %s, %s, %d, and %f for string, decimal, no, integer and float. And then wherever you want to store it to. Cool. And just for a sanity check, I'll just print this out for you for now to see that it actually works. Actually, I'll just print out 2 of them for you. What the? See you, Lucas. Where did I got rid of my scanf. Oops. Okay. Let's just say 1. Whoops. That really frustrates me. Okay. So that was our sanity check. It works. So this string got stored into user input. And then with scanf, we can say, hey, take that string that we just got, split it into these 4 things: a string, a number, and a float. So even though you pass this in as a string, it automatically casts it into an integer for you, which I think is quite cool. Any questions on that so far before we move on? Nope. Okay. So we have all the data that we need. Now we just need to actually create the superhero, right? Remember, we only have pointers so far, so we need to actually allocate space for the new superhero that's coming in. So this allocates enough memory for one of these structs. And when you first create the struct, remember everything is empty or garbage values. So we need to actually copy in the data that we split here into the struct itself. Don't forget, with strings, it's not as easy to just go like that. Why is that the case? Why can't I copy the string in like this? Go on. Yes, you have to use string copy. But C, unlike Python or any other language, you can't just point strings from one to another. You have to actually copy the string. So you have to use struct copy. And struct copy is quite easy. It's just the destination and then the source. And I'm going to do the same thing for but with every other data type though, it's fine. So we've allocated memory for a superhero, but then we have to actually put it into the array that we've created here. So superheroes I go to new hero. All right, so that does the creation of the superhero so far. Any uncertainties to this point? Yep. Okay. Let's try to wrap this up. So something we haven't talked about yet, files. Files I like to think are not too bad, but I understand if it can get a bit confusing because there are so many functions that kind of almost do the same thing. So there's like so many ways to write to a file, so many ways to read from a file. It can all get a bit confusing, and it doesn't really matter which one you use as long as you're comfortable with it. But with files, whether you're writing, opening, appending, whatever, you have to use a file pointer. It's defined as this macro. It's already in standard input output, so you don't have to worry about defining or whatsoever. I'm going to call it file pointer. To open the file, you use fopen. And then I'm going to say superheroes.txt. So it's text file. And then there are so many arguments that you can give. There's W for write, R for read. You can do W plus, R plus, I believe, as well, if you want to read and write. And then if you add in the B, that says you're reading it as a binary file. So many ways. I don't know at the top of my head, but that's fine. Okay, so we've opened a file for writing. And with file pointers, it's good practice to check if you were actually successfully able to open the file. So if it's equal to null, fprintf. This is also another function that's good to know. Fprintf is used to print to file streams. So not only the files you create themselves, but it also includes the error commands on the terminal. So the file stream that the terminal uses for errors is called std error. So that's why I put it here. And then you can put the message, something like couldn't open file, which shouldn't happen, but just in case. And then you can exit your program, I guess. So we've opened our file, right? And what do we want to put in the file? We want to put the name and then a number that we get from bitwise operations. So for quick refresher again, what we want to do is we take the number that comes with our input, so 38 here, and then we want to mask bits 2 to 5, and then we want to put that into file. So let's do the masking part. So a mask is just a bunch of ones in the bits that you're interested in. So if you're interested in the least significant bit, your mask is just a simple 1 because 0, 0, 0, 0, 0, 1. If you're interested in the middle bit, everything else is 0, and that middle bit is a 1. Right? So in our case, the mask is bits 2 to 5. So 7, 6, 5, 4, 3, 2, 0. Okay, this is our mask. So this gives us a region of interest of bits 2 to 5. And then we want to mask something, we have to AND it, bitwise AND it. And the reason why bitwise ANDing works is because 1 and something is whatever that something is, if that makes sense. If you have a 0 and you AND it with a 1, you get 0. If you have a 1 and you AND it with a 1, you get a 1. So whatever is there, if you AND it with a 1, you just get that number again, which is why that's useful for bit masking. I hope that makes sense. If that doesn't, just raise your hand. Get it, Ben? Cool. Okay. All right. So now we want to go through each superhero and then perform these bitwise operations. So to keep track, I'm just gonna declare 2 variables here. I guess it's a bit unnecessary, but it's fine. So the number, let's works like this. So going through each element in the dynamically allocated list, accessing each pointer to superheroes, and then we're grabbing their year, and I'm storing it in number. So to do a bit masking, we do number and mask. So I hope this makes sense. This is the bitwise AND that I mentioned before. We want to assign it to something, we do it here. One thing we have to note here is with 1 0 1 0 0 1 1 0, if we AND it with this, don't forget we get 1 0 0 1 0 0. We don't want these trailing zeros, so you're gonna have to bit shift it to get the number that you actually want. And bit shifting is literally just moving bits from their position to another, either to the left or to the right, by however many positions that you specify. In this case, because we're taking bits 2 to 5, you get that extra trailing bits at the start. So we want to bit shift by 2 to the right. Does that make sense? So we can do new number. So do like that. And then to actually write to the file, we're going to use fprintf. There's so many ways to write to a file, but we're going to use fprintf. Use the file pointer, and then we're going to write the name and then the number from the bitwise operation. So %s and then %d, and with a new line. So and once you're done with the file, don't forget to always close it. And then something that I mentioned was once that's done, print how many superheroes are accounted for. So I'm just going to print something like that to show that my program's done. So no text file here. well, there's the outline text, but no superheroes text file here. I'm gonna compile it. Whoops. There we go. Need to actually access the here. Okay, I'm gonna say 3 to match what I have here. Bear with me. Great show, by the way. Recommend the second one. Where am I? We'll come back to that in a bit, but let's see if the text file is correct. Cool. We got the numbers that we expected. So these are the bitwise operations result. I hope they're correct. I like to think they're correct. I'm not going to verify them. I'm just going to assume they're correct because I'm not going to waste time. As for this, what happened there? Because I did not specify the actual number that I'm printing. Okay, cool. So that's what happened. We took a string, and then based on how many numbers there are, we dynamically allocated an array of pointers to structs. We split the string using scanf and fgets. Did some string copying. We opened up a file to write. We did some bit masking, bit shifting, and then we closed the file. That might be it. Any questions on that? I do not. I guess like just the tutorial questions, I suppose. This is something I just came up with in the spur of the moment. So yeah, yes. I do not have that information. As in, I don't know what Mitch thinks. I could ask him, but I think he's more on the side of not releasing, if I'm not mistaken, mainly because these are assess tutorials that get used like almost every year now. I know it sucks, but I think that's what he's going with. Yeah, you might want, maybe you can post again, but I'm not at the liberty, nor do I have the power to release solutions. So you might want to ask him again. So if you want any other example questions, the tutorials are your best bet. Okay. All right, anything else? Because that might be it. And we're coming up to just about 2 hours from when we first started. Yeah. All right, that is a wrap then. We'll end it here.